The last thing we're going to talk about in this chapter is how to generate energy using chemical reactions. So these redox reactions that we've been talking about, we can actually harness the movement of those electrons to generate electricity. In order to determine what would make a good battery or not, or what things should be used together to make electrical energy, we use something called an activity series. So an activity series is a ranking of metals and hydrogen in order of how easily they lose electrons, so how easily they are oxidized. And so here we have a list, and you're going to generate a list similar to this in class using an online simulation of how these metals react with each other and in different solutions. The way we can use this in determining if chemical reactions are going to be spontaneous or not, meaning will that reaction that we've written happen, we can write it, but will it actually occur, is using this activity series. So here for part A, we have zinc plus H plus, 2 H pluses, going to zinc 2 plus plus H2. So the things that are on our activity series are zinc and the H2. So you can see zinc is right here on our table between aluminum and chromium. It's about about a third of the way down. And then hydrogen, H2 gas, is almost 2/3 of the way down. So it's quite a bit lower on the list than the zinc is. And so that means that zinc is more easily oxidized than H2 is. So in this reaction, zinc is the thing that's oxidized, and H2 is the thing that's reduced. So as long as the thing that's oxidized is higher on the list than whatever's being reduced, then the reaction will be spontaneous. So part A is spontaneous because zinc is above H2. All right, the second one we have here is copper with H2, making Cu2 plus H2 gas. So if we look here, H2 is just above copper on our activity series, which means that H2 is actually more likely to be oxidized than copper is. And since copper is the thing oxidized in this reaction, it will not be spontaneous. It will not go forward. Now we can use this information in these reactions to generate electricity. So an apparatus that generates electrical energy from spontaneous oxidation reduction reactions is called a voltaic cell. And there are two components to our voltaic cell. The first is the anode, and that is the metal that's being oxidized. And then the cathode is where the reduction takes place. So electrons always flow from the anode to the cathode because oxidation produces electrons because they've been lost, and reduction gains electrons, so that's where the electrons go. So we can harness the power of this reaction by directing the electrons along our wire, and the movement of electrons along a wire is just electricity. All right, so just one other note before we go into the specifics of what's going on here. Anode is where the oxidation happens, so you can remember anox, and cathode is where the reduction happens, so you can remember red cat. Those are just two little mnemonics, I guess, to help you remember which one happens where. All right, now if we zoom into this voltaic cell, you can see all the different components. So in the oxidation half reaction, we have the anode, which is zinc in this case, and we also have it in a solution of ions of that particular metal. So in this case, that's zinc 2 plus ions. All right, there's some sulfate there, but the sulfate really doesn't matter. It's just a spectator in this reaction. All right, and then in the other half, we have the reduction reaction. So we have the cathode, which is the copper metal, and then we have ions of that metal as well. So in this case, copper 2 plus. All right, in order for this to happen, we have to have a wire that connects the anode to the cathode. All right, and that could have something in it, so we could have the wire go through a light bulb, for example, and light a light bulb. And then we also need a salt bridge. So the salt bridge prevents the two reactions from getting a buildup of charge, which isn't allowed. So if we were to keep moving electrons, which are negatively charged, from the anode to the cathode, we'd eventually get, or relatively quickly, we'd get a buildup of positive charge in the anode half reaction, and we'd get a buildup of negative charge in the reduction half reaction. So the salt bridge is a tube that's filled with an aqueous solution of some salt. It just has to have positive and negative ions. They don't participate in the reaction, but they're necessary to keep the charge balanced. Okay, and then the last thing I want to say is just that I don't use this very often, but you might see it on the SAT if you take the subject test. There's a shorthand notation for talking about voltaic cells, and the way you do that is you write whatever the metal anode is, so in this case that's Zn solid, and then there's a line, and the Zn2 plus, okay, because that's our first reaction over here. And then there's two lines, which represents the division between the two half reactions, and then Cu2 plus, which is aqueous, and another line, and Cus. Okay, so this is just a shorter way to represent the reaction that's happening above. So I'm not going to make you generate that, but if you see that, you should know what it is referring to in terms of a voltaic cell. Now, there are lots of examples of how we use these reactions in everyday life, and I'm just going to go through two of them just for the sake of time. So the first is a lead storage battery, which is what you all have in your cars out in the parking lot. So the way this works is we have lead and we have an acid. So the two half reactions are a little bit different because only one of them involves the metal. So the oxidation reaction here is lead solid plus the sulfate ion going to lead sulfate plus 2 electrons. Okay, and you can see here hopefully that the lead is going from a 0 oxidation state to a plus 2. So it is oxidized. And then the cathode reaction is 2 electrons with 4 H pluses and lead oxide, which has a plus 4 charge, plus SO4 2 minus, going to lead sulfate and water. Okay, so then this would be our overall cell reaction. And then as we run your car, what happens is the alternator recharges your battery, and so then the next time you go to start your car, you have enough charge in the battery to start the car. And so cars take a good bit of energy in order to start, which is why we need these batteries. But luckily the way they work recharges the battery, and so you can continue to start your car over and over again on the same battery. Eventually, it will lose the ability to recharge, and that's when people have to replace their car batteries. And occasionally, if you leave your headlights on or something like that, you can end up with a dead battery because even when you're not using the car, the battery is running. So that's how they work. And the last kind of battery I'm going to talk about is just a dry cell battery. And a dry cell battery is a battery that uses paste rather than an aqueous solution. So there's actually liquid acid solution in the lead storage batteries that we just talked about. But in the dry cell batteries, these are like AA batteries or 9-volt batteries, the kind that you buy to put in things like flashlights, for example. They don't have a solution in them, they have a paste. Okay, and there are multiple ways this can work. I'm only going to talk about the kind that is used in ones that are in acidic dry cell batteries, since we focus just on balancing under acidic conditions. But alkaline batteries, for example, are under basic conditions, because alkaline means basic. So for today's purposes, I'm only going to talk about the reaction that's happening in this particular battery here. So you can see that we have zinc metal, and it is going to be oxidized to zinc 2 plus 2 electrons. So that's our oxidation reaction, really simple. And then the reaction that happens at the cathode is the oxidation of MnO2 to Mn2O3. And so the half reaction for that is 2 electrons plus 2 MnO2, which is a solid, plus 2 NH4 plus, and that ammonium ion is in that paste, goes to Mn2O3 plus 2 NH3, which is aqueous, plus water. Okay, so when you combine those two reactions, this is your overall reaction. And I'm not telling you this because I want you to memorize it, but just to give you a sense of how these reactions are used in everyday life. You use them on a daily basis. Okay, so it's a similar process if you look at mercury and lithium batteries and nickel and cadmium batteries, which you use in other things. In the nickel cadmium batteries are what you can usually find in cell phones, for example. So these are all over the place. Some of them are rechargeable, meaning that you can hook them up to electricity and make the electrons flow back the other way, and then have the ability for the electrons to flow again from the anode to the cathode again. All right, so this wraps up our discussion of batteries and the use of oxidation reduction reactions in your everyday life.